About 13.8 billion years ago, the hypothetical Big Bang gave birth to our universe. At the time of birth, our universe was smaller than a grain of sand, but now it has evolved into a tremendous size. The universe is so massive that even the fastest traveling light gets lost in between. Even the photon from our sun takes 4 years to reach the nearest star, and for it to travel to intergalactic universes, it takes millions of years. We can't see the edge of our universe or measure it, and that's what makes it interesting. Before we find out about the edge of the universe, we don't even know what lies outside of our observable universe. But first, let us tell you, universe and observable universe are two different things. Observable universe is a sphere around us that we can observe at present time. It's not because of our technology, but because of limitations created by the speed of light. As the universe is isotropic and expanding faster than the speed of light, anything beyond the observable wouldn't get enough time to reach us. No signal can travel faster than the speed of light, which means that there's a maximum distance beyond which nothing can be detected, also called the particle horizon. So, how big is the universe, and what lies on the edge of the universe? If you like our videos, please support us with a thumbs up and subscribe to our channel, and look forward to the video that will be waiting for you in the future. Our solar system is a tiny planetary system located on the Orion arm of the Milky Way. For us, our solar system is so massive that our satellites launched in 1977 just reached the outside of our solar system in 2012. On the 1st of August 2012, NASA confirmed that Voyager 1 entered interstellar space, which was later followed by Voyager 2 in 2018. These are the only two man-made objects that ever traveled outside of our solar system, and it took them about 44 years, roughly. Voyager 1 has traveled 14.4 billion miles so far, but when you compare this with the vastness of the universe, it's nothing. Well, it's practically impossible to find out what lies beyond our universe, but some of the astronomers have stepped up and proposed some theories and predictions on what lies outside of our universe. Let's start with the observable universe and what lies beyond the edge of our observable universe. Hubble volume is the spherical region of the observable universe beyond which we cannot see, as the rate of expansion of the universe is higher than the speed of light. Simply put, light beyond the Hubble sphere does not get enough time to reach us. We can never see further than the Hubble sphere. Astronomers estimated that the oldest photon we can observe has traveled about 45 to 47 billion light years. This means the observable universe is 93 billion light years large, give or take a few billion light years. All the photons, light, stars, planets, black holes we observe lie within these 93 billion light years. Scientists predict the universe is the same outside of this as well, but we cannot observe it. Astronomers believe that space invisible to us is just the same as our observable universe. They predict that there are other stars, planets beyond the Hubble volume, and if you go to the edge of our Hubble volume, there you'll find another Hubble volume just the same as ours. This may seem hard to believe, but the infinity of the universe is beyond the imagination of humans. The next prediction about the universe has to do something with curvature. Cosmologists are not sure if the universe is infinitely big or just extremely large. To measure it, they need to instead look at the curvature. If the universe is geometrically flat, then it can be infinite, and if it's curved like Earth's surface, then it has finite volume. Current observations and measurements of the universe tells us it's almost perfectly flat. You might think this means that the universe is infinite, but it's not that simple. Even in the case of a flat universe, the universe doesn't necessarily have to be infinite. For example, take a cylinder. This is a shape that is geometrically flat because the parallel lines drawn on the surface remain parallel, yet it has a finite size. The same could be true for our universe, but currently we have no way of testing that, and it doesn't really affect day-to-day operation of the cosmos. The next theory is infinity bubble, where each bubble contains a universe similar to ours. The Big Bang could have made infinite numbers of bubbles, and each bubbles are infinite within itself, meaning we can't see past through our bubble as universe is expanding faster than the speed of light. There could be another Earth inside another bubble where a different version of you has already been subscribed to our channel. Wink wink. Another theory deals with something called dark flow. In 2008, astronomers discovered something very strange and unexplained. Galactic clusters were streaming in the same direction at immense speed, over 2 million miles per hour. One possible cause, massive structures outside the observable universe exerting gravitational influence. As for the structures themselves, they could be literally anything. Amazingly huge accumulations of matter and energy on scales we can hardly imagine, or even bizarre warps in space-time that are funneling gravitational forces from other universes. We simply don't know what these massive objects could be. Notably, recent analysis have claimed to debunk the dark flow model, but this debunking is still being disputed. The next theory is black hole spawning, known as the Fecund universes theory, suggests that every black hole in our universe causes the formation of a new universe. Each universe will have slightly different physical laws than the former universe. In this way, Smolin suggests a sort of natural selection for universes, as laws that lead to the frequent formation of black holes lead to the creation of more universes, while non-black hole forming universes die out. This theory has since been discontinued by Smolin himself and others. These ideas are just a few of the more popular hypotheses. There are a lot more out there, but none of them are proven yet. Since our view is so small and the universe is so vast, we may only be able to imagine what is there. We may only be able to see the after effect on a large scale and theorize what's causing it. Since the universe expands faster than even light can travel, we'll likely never be able to reach or see the border. What lies beyond may remain a mystery even long after humanity has perished. And while the current expansion and passing of time reveal new galaxies and stars whose light just starts to reach us, these newly found stars and galaxies will become dimmer due to redshift as light has longer to travel. The furthest stars and galaxies will simply turn invisible. Whether it's a multiverse, a great nothing, or another galaxy outside of a black hole, we'll likely never learn the answer to it. We're left with speculations and theories about what lies beyond. What do you think? Does another unknown world exist outside our universe? Does infinity exist? And if so, how infinite is it really? The Big Bang Theory is our best guess about how the universe began. It simply means that the universe began with infinitely hot and dense single point, which then inflated and stretched. When we look out into the distant galaxy, we see that they're all moving away from us. Our technology doesn't allow us to look back at the universe's birth, and much of what we know about the Big Bang comes from mathematical formulas and models. So, did the Big Bang actually happen, or is there something that's still out there hiding from us? The majority of the astronomical community accepts the theory. However, there are some theorists out there who have an alternative explanation rather than the Big Bang. There's really no doubt that at some level, the Big Bang Theory gives us an accurate description of the earliest stage of the universe. But how accurate? What part of the story are we absolutely sure about? And what part is still genuinely a question? The universe is expanding. Light from distant galaxies is red-shifted and stretched to longer wavelengths, and the further away the galaxy is, the more its light is red-shifted. In context with the theory of relativity, the only sensible reason for this is the fact that the universe is expanding now and light traveling through space is stretched. So this means that the universe 5 minutes ago was smaller than it is now. If you change that 5 minutes into a billion years, it means the universe was smaller. The further back you go, the universe gets much smaller, which means once upon a time it was tiny and compact. 400,000 years after our hypothetical Big Bang, the entire universe was still as hot, opaque, and dense as the inside of a star, as it was full of protons and electrons. A plasma. As the time went on, the universe expanded and became much colder. This plasma slipped into a gas as the first hydrogen atoms formed, and at the same moment, the infrared light trapped inside plasma was free to travel to the cosmos. And it's still traveling today, but it's no longer infrared anymore and stretched into microwaves. But the good news is we can still see it. It's called cosmic microwave background, or CMB in short. We'll talk about CMB in more detail in the next video, but for today, let's just emphasize that this radiation is almost impossible to explain without a universe that was much smaller, hotter, and denser. So at least that far back in time, the Big Bang Theory is right. When we look at galaxies from vast distances, we're also looking back in time. We see that these very first galaxies are very different from our galaxies, and this proves that the universe is also evolving to some extent. But all of these only get us back to 400,000 years after the Big Bang. But we can rewind further to the very first second after the Big Bang. At the first few seconds after the Big Bang, we predict the universe was much smaller and hotter and denser, allowing atoms to undergo nuclear fusion and create heavier elements in a process we call primordial nucleosynthesis. The Big Bang Theory tells us how long these elements were fused and at what temperature, and also predicts the proportion of deuterium, helium, and lithium that should have been formed. It's on startling agreement with what we see out there in the universe now. The Big Bang Theory has strong, powerful, and direct evidence almost down to the first second, but it simply can't explain what happened on that very first second of time. Our understanding of physics is very good, down to the Earth age of 10 to the power of minus 32 seconds when the entire universe was around the size of a grain of sand. This is because we have recreated this condition of the universe at this time. We have recreated these insane energies in our particle accelerators. We checked that our physics works under this condition, so we have a lot of confidence in the Big Bang Theory. However, this is where our certainty ends. Earlier than 10 to the power of minus 32 seconds, we just can't produce the energy needed to test our understanding of physics in those conditions. But the major confusion lies within that very first second of our universe. How can something come out of nothing? Let's ignore that part for now, as the Big Bang Theory itself can't explain it. The Large Hadron Collider located in Switzerland helps us to unravel the mystery right after the Big Bang. It pushes protons, or ions, to near the speed of light inside a 27-kilometer ring of superconducting magnets. After the discovery of the Higgs boson in the Hadron Collider, it proved the existence of an invisible process that gives all particles their mass or substance. Practically, it has not changed anything in our life, but it's a huge step on a journey towards understanding how the universe works. Fast forward to the first 400,000 years after the Big Bang. The universe is quite bigger now, but it's still about 1,000 times smaller than the modern universe. It's full of hot hydrogen plasma, but at 400,000 years, it cooled down to a state where it formed the first atoms and released cosmic background radiation. We now see this light as almost perfectly smooth, but that smoothness only has one explanation: that when the radiation was released, the universe was almost exactly the same temperature everywhere. Let's look at this example. When you add milk to the tea, it'll smooth out and become the same temperature after a bit of time. Well, the universe works on the same principle of heat transfer. But when the cosmic background radiation was released, there had not been enough time for this mixing to have occurred, and the universe to reach a uniform temperature, which is why it's so weird. The distinct path of the universe on this direction to have the same temperature and density on that direction, there needs to have been enough time for something to travel between these points, and there wasn't enough time even for light. Let's take this grain of sand sized universe at 10 to the power of negative 32 seconds. The photon emitted on the one side of the grain wouldn't have time to get to the other side, not even in 400,000 years. Although light is fast, the opposite ends of the universe were traveling apart even faster. There are a lot of things that the Big Bang Theory simply can't explain. However, the aspects of the expansion of the universe under this theory is so hard that we don't know if the basic picture is right. In this sense, we shouldn't call the Big Bang Theory as the theory of the origin of the universe, but as the theory of the expansion of our universe. However, as with every well-established theory, there are boundaries for what the Big Bang actually explains. Those boundaries are taken for granted all the time, as we don't have another better option to explain this. Hopefully one day our technology will advance, and these boundaries will be solved and help us to encompass a true origin of what we are and what our universe is. Well, someday it's also possible that we find out a new theory that has more evidence and falls within our understanding of physics. For this to happen, we need to wait and watch. Perhaps we should be exploring near home first and find out how life evolved in our solar system itself.